Hello students, so let us discuss about the potential due to continuous charge distributions. Potential due to continuous charge distribution. Continuous charge distributions are line charges, surface charges or volume charges. So let us start with an arc. If you have an arc whose total length is L and it has a charge capital Q, the total charge is capital Q. You want to calculate the potential at the center, right? So potential at center of arc. Now potential is a scalar. So here the charge is uniformly distributed along the curve and the charge per unit length is lambda, which is now Q by L, right? Charge per unit length. Now let us consider a small portion, elemental portion. It is also at a distance r from this point. So let us say this has a charge dq, small charge dq. So dq can be given by lambda into, this is charge per unit length, into its own length, which is, you can take it as r d theta. If it subtends an angle d theta, small angle is d theta, r d theta is the length of this small arc. It is as good as a point. If d theta is very small, that means the length of the arc is very small, that it is close to like a point, very small. So now the potential due to such an elemental charge, this is elemental charge. The potential at center due to elemental charge is dV is the small potential is kq by r. Q is dq by r is the distance r, right? So if you want to calculate the total potential, you have to integrate this equation. Now let us find the total potential. Integral dV is equal to integral k dq is lambda r d theta by r. D theta varies from one particular angle to the other one. Now observe this, as you integrate theta, this is from, let us say theta is measured from a particular line, this is theta, let us measure it anti-clockwise from this edge. So this will be the small angle d theta. Now what is the variation in theta? The smallest value to highest value, right? So the smallest value for theta is 0, then this charge is included. As you increase the theta, all these portions are covered. So our integration should be carried from 0 to a particular value theta. Let us say alpha is the length of the arc, sorry, angle of the arc. Alpha is angle subtended, the total angle subtended by the arc. So now what is the integration variable? 0 to alpha, right? So this will be k lambda by r cancels off, d theta integration, it gives you alpha, right? But lambda is q by L, that is k q by L is r alpha again. So this is r alpha into alpha. This gives you kq by r. You notice this, the potential is coming out to be kq by r. Why this is happening? Observe, the points, the charges are all at the same distance r from the center. They all have equal distance. So the potential contributed by each one, k dq by r, is added simply. So straight away from this equation you can actually integrate the small charge dq, and you can write it as kq by r, because there is a symmetry. All the charges are at a distance capital R from the required location, which is the center of the R. So it is kq by r. Now whatever the angle is, it doesn't matter, we are getting kq by r. So if the arc length is even more, right, let us take this kind of an arc. Now at the center, what would be the potential? If q is the total charge, then you can straight away write it as kq dash by r for arcs at the center. So always for arcs it is like this. Now what if the arc is complete? It will become a ring. So potential at center of uniformly charged ring. The second one. So now the ring is uniformly charged. You can straight away write it as, if the total charge is kq, it will be kq by r again. R is the radius. At the center, it is very easy to calculate the potential at the center. It is difficult to calculate the potential at any other point because the distance will be different. Suppose you take this location, which is exterior to the circle. Now the distance from the charges is, this is closest and this is far, and this is even far. So the distance here varies and it becomes difficult to integrate. But at the center it is very easy. It is kq by r. This is for a uniformly charged ring. All the charges equally at the same distance from the r. Now another case, potential at center of non-uniformly charged. Non-uniformly charged meaning it has different charge density. That means the pluses here are maybe more denser, then here maybe they are so weak. Again there is some density again. This is non-uniformly charged. So much charge is located in this region, less charge is present here, again less charge and more charge. So it's non-uniform. But even then, in this case, if you consider any small portion of the charge, it is at the distance r. So to carry out the integration, if you write k dq by r for an elemental charge and integrate it, you will get it to be kq by r if the total charge is q. Why? How can we do this? We can directly add the total charge. K by r is a constant and integral dq gives us total charge q. Why this is possible? Only because even though the charge is non-uniformly distributed, the potential due to each elemental charge is the same value. Wherever the charge is, whether the dq is here or here, it will give the same potential k dq by r. And if you sum up all that, you will get kq by r. So this is interesting result. For even uniformly charged or non-uniformly charged, we get the same value of potential at the center. Now let us discuss about the potential due to ring at an axial position. On the axis of the ring, we want to calculate the potential at any particular location, which is at a certain distance from the center. So potential at a point on axis of ring. So if the ring has total charge q, again radius r. Now by symmetry you can solve it very easily. If you take an elemental charge, what is the distance of the charge from this location? This is our point P. We want to calculate potential at point P. So this distance is hypotenuse. So it is Let us say this is x, this is d. So now d is root over x square plus r square. This is the distance of the elemental charge from the point P. Now what is the potential? K q by r, but r is the distance here, it is root over x square plus r square. This is the small potential dV. Now observe, this distance will be same for any charge on the ring. Any elemental charge you take, the distance will be the d, which is root over x square plus r square. You will form a right angle triangle, right? Imagine it in 3D. The distance from any point on the ring to the axial point will be same. They are symmetrically placed on the circle. So in this case also, because the distance is always the same and the potential is a scalar, it is not like electric field, it is not vector. We need not worry about the direction, and we need not take the components. That is completely different. The electric field was a vector, so to calculate the net field we had to take components. But here it is just potential, it is adding some potential to this point, right? Just a number. So if each one adds 1 unit, all the elemental charges add up. So 1, 1, 1, 1, all such elemental potentials add up and they give the total potential. It's a scalar value. So if you just integrate this, the potential at P will be K q by R. So Q is the total charge Q, but the distance is now root over x square plus r square, right? All the charge is at a same distance. All the charge on ring is at same distance. Same distance from required location. Where you want to calculate the potential. So this is the idea. If you want to calculate the potential of any such system, continuous charge distribution, if, try to see if there is symmetry. If there is symmetry, if the charges are at the same distance, then you can straight away write a kq by the particular distance. What if the ring is now non-uniformly charged? If it is non-uniformly charged, that means on the ring now the charge is denser at some locations and rarer at some locations. So this is non-uniformly distributed. Even though it is non-uniformly distributed, now again for the actual point, any point here, the distance will be the same thing. So it will be again kq by, if this distance is x and this is radius r, it will be root over x square plus r square. So whether it is non-uniform or uniform, let us say this is uniformly charged. Whether it is uniform or non-uniform, we have the same value for the potential. Right? Remember these things. Let us solve a question now. Find potential at origin due to charges which are placed on x-axis as shown. So charges of equal magnitude q naught 1 coulomb is placed on x-axis at locations 2, 4, 8, 16 and so on. So powers of 2, right? Again the next charge will be at 32. So on. Now you want to calculate the potential at origin. Due to one charge, it will be kq naught by the distance, just the distance. You don't have to add direction to it. Q naught by 2 plus kq naught by, this distance will be 4, kq naught by, this is 8, so on, up to infinity. Charges are placed up to infinity in such progression. Now this is the total potential. You take kq naught, so this is 1 by 2 plus, you can write it as 1 by 2 square, 1 by 2 cube and so on, right? So this is a geometric progression, right? So here a value is half and r is also half. right? AR, AR square, AR cube, and so on. So if the sum is up to infinity, we know it is A by 1 minus R, the sum. So this is equal to half by 1 minus half, that gives you 1. So the potential here would be kq naught by 1, kq naught. So this is the total potential. K value is 9 into 10 power 9. So this is 9 into 10 power 9. Q naught is 1 coulombs SI units volt. So that is the total potential contributed by all such charges at the location which is origin. The topic which we now discuss is very important. It's relation between field and potential, E bar and V. So we now discuss the relation between a vector and a scalar, right? For a conservative force, whenever you have a force which is conservative in nature, now there is two things associated with this conservative force: a field and it has a potential. So this gives rise to potential energy idea, and this gives the force acting, actual force which is acting. So now we know that force 2E bar, right, and the potential energy QT, right. So what is the relation between these two, the field and the potential? So it's given by this: dV is minus integral E dot dr, or you can write it in another way: E bar is gradient of the potential. This operation is called gradient. Okay. It is a vector operator. This means it is performing an operation which is like this. It is dou y dou x I cap, dou y j cap, dou y dou z k cap on the potential. So this means this operation. That means we are now multiplying the scalar with an operator. It performs operation on this in such a way that now it becomes a vector, right? So what does this give you? If you expand it, you will get dou v by dou x. See, it is an operation. You are performing a partial derivative operation on v in I direction, right? So it is differentiating the potential with respect to position, which is x, in the dimension I cap, in the direction. So this plus dou v by dou y j plus dou v by dou z k cap. So after performing this operation, you have this. You are differentiating potential function. V is some function. It can be a function of x, y, z. See, the potential is all around the charge, right? It is three-dimensional space. So the potential is also like a function which has x, y, z variables. So whenever you have such a function, potential function given, if you want to calculate the field, you can use this relation. One correction here, sorry. E bar is negative of the gradient of potential. So now if you want to calculate Ex, you can expand this also. See, E bar is equal to Ex I cap plus Ey j cap plus Ez k cap. That means electric field is a vector, right? So if you draw in 3D, a field vector E bar, it has three components. One is Ex, the other one Ey. These are X, Y, Z axis. Now there is another component Ez. So E bar is expressed as the resultant of these three components Ex, Ey, Ez. So now comparing this with this expression. So let's write this expression again, d dou v by dou x I cap plus dou v by dou y j cap plus dou v by dou z k cap. But the negative of it is very important. It is the negative of this value. So comparing these two, now you have Ex equals minus dou v by dou x, Ey equals minus dou v by dou y, and Ez equals minus dou v by dou z. So by definition, this is how they are related, right? Just understand what these expressions mean. I will explain what they are. For now, get the terms. So this is called a gradient operation. It converts a scalar into a vector. Gradient operation converts a scalar into a vector. So this is what gradient does. If you take gradient of a scalar, what you get as a result is a vector quantity. Now the field at any particular location, right? There is a system of charges. Due to these charges at this point, let us say we have a net field bar. How do you estimate, how do you get the idea of the field? You can get it from the potential function. If you know the potential due to all of them, you can estimate the field at that location in x, y, z directions, right? So how do we do that? All you need to know is potential function. So what do? You perform this operation. You take partial derivatives with respect to x and with respect to y and with respect to z. Negative of those values will be x components for x component, y component, z component for the electric field correspondingly. That's one important result. Or you can see it in the same way, because this is written, generally this is written as E bar equals minus dv by dr. Forget about the bar. So E in a particular direction, radial direction, is generally written as minus dv by dr, right? If you have to express it radial direction, right? Radial means you have a charge, let us say charge q. Now from this point you have a radius vector drawn. At any point you want to calculate the potential or field. That particular direction is radial direction. Now you know that aq by r square is the field in the radial direction. But how are you getting that? You can perform this operation again. It is minus dv by, because this is only radial direction, now we write it as dv by dr. If you have x, y, z and you have to take partial derivative, you have to write it as dou. Dou implies partial derivative. This is normal derivative. D by dr of, negative of d by dr of what? Potential. What is the potential due to this? aq by r, we know that. So what are you getting here? So this is r power minus 1, 1 by r square. So this term is aq, you have to differentiate d by dr of 1 by r. What do you get? Negative of that. So this is minus 1 by r square, right? So from this you get kq by r square. So even if you have to do it in radial direction, this works, right? The field is kq by r square. How are you getting it in radial direction? By taking the negative derivative of the potential, right? This is minus dv by dr. This is how it works. This is how they are related, right? So changing this equation, we can find dV is minus E dot dr, but delta V, if you have to calculate the change, a bigger change, now we have to integrate it. So this delta V is represented as this. So these two are standard definitions which relate the field and potential. So this is change in potential in radial distance. This is the field at a particular point. How are they related? The field can be given by negative gradient of potential, and you can calculate the potential difference between 2 points. See, you can do it from A to B, right? You want to calculate potential difference between any two radial locations. See, this is a point P. If there is a point Q also somewhere, okay, let's write it in a different light. So from the point P, point Q again, there are 2 points P and Q. If you want to calculate the potential difference between those two, then the delta V, the potential difference between them, can be estimated with this equation. It is minus integral E dot dr, right? You integrate it from a certain limit to another limit. So that's how you get the potential difference, right? So the important equations are these. If you want to calculate the field in x and y and z directions, you can use that. If you want to calculate the field in radial direction, you can use this directly without x, y, z. It is simply the derivative of potential in radial direction, dV by dr, but negative of it. Always remember, it is the negative of the derivatives. If you want to calculate the potential difference, you can reverse this, right? dV can be expressed as minus E dot dr, and we can integrate this. So let us see how these equations are useful. We will see one by one all of these equations, right? How we are using these 4. So one equation we have already used. How? This one. To check the potential and field relation for a point charge. See, this is working. The field is given by minus dV by dr. You obtained the field finally. This is the field. We are operating by performing this operation minus d by dr on the potential function. We get the field. So let us see other cases also. Let us see a question. The potential in space is given by V. The potential function is given as a function of x, y, z. There are 3 variables. So it is given as 3 into x plus y plus z. Find the expression for electric field at a point x, y, z. So in 3D space, we have no idea how it is, but the mathematical expression is known. So the potential at any point in the space can be calculated with this expression. For example, if you want to calculate the potential at 1, 2, 3, we have a point P 1, 2, 3, which is somewhere in the space here, right? 1 units from this, 2 units and 3 units coming out. So at this point, if you want to calculate the potential, it is given by this SI units. Let us say it is SI units, volts. So what would be the potential? It is 3 times 1 plus 2 plus 3, which is 18 volt. So potential is expressed as a function now, as a function of x, y, z variables, right? Do you understand this first? So it is a function of x, y, z. It need not be expressed in x, y, z all the time, but in this case it is given like this. Now from this information, if you want to calculate the field at any point x, y, z, so you will take random point x, y, z. At that particular point, what is the field vector? So we get that directly, the E bar at such a point by this. You can estimate the components. Ex is given by minus dou v by dou x. Ey is given by minus dou v by dou y. And Ez is given by minus dou v by dou z. Negative of the partial derivatives. So do this operation, minus of dou by dou x of this expression. V is 3 times x plus y plus z, that is 3x plus 3y plus 3z. So now remember, we are taking partial derivatives. That means if you want to calculate this, it is minus dou by dou x of 3x plus 3y plus 3z. So while taking partial derivatives with a particular variable, now our variable is x here. We are taking partial derivative with respect to x. So in such case, y and z becomes constants. So that is the idea of partial derivative. So in this case, differentiating the first time, you will have minus 3. Because derivative of 3x is 3, but for 3y and 3z they are as constants now. So with respect to x, if you take partial derivative, they will become 0, so it will be minus 3. So ex is minus 3. Similarly, if you do, ey will also be minus 3 and ez will also be minus 3. These are the components of the electric field vector. Now if you want to form the vector itself, E bar can be written as ex I cap plus ey j cap plus ez k cap. So that's how we form the vector. It is minus 3i plus 3j plus k. So this is the vector at that particular point, the field vector. Let us see a particular case of uniform electric field. So in this region, let us say in this room itself, the field is going from negative infinity to positive infinity along the x-axis, right? So this is our x-axis. Now field is going towards x-axis and it is uniform field. That means the magnitude at any point is the same value and it is particularly directed along one particular direction. So there is uniform field of magnitude E. The field magnitude is everywhere the same. E in directed and a positive x direction. So that is uniform field. So that field can be represented by uniformly drawing the field lines. So those are the field lines. So this is x-axis, this is y-axis, xy plane. We are seeing it in 2D. We are only interested in one dimension actually. For now we are discussing the thing only along x-axis. Let us see how this is. So the field is directed only in x direction, right? Now what do you understand from this equation? Delta V equals minus integral E dot dr. So if you have the field vector properly, then you can take the potential difference, right? Or in one dimension, we are doing it in one dimension, so we can write it this way: dV equals minus E dx. This is obtained from this, the partial derivative. But here, since we have only one dimension, I am directly writing it as dV equals minus E dx. But this is E bar dot dx bar, the dot product of these two vectors, so that it becomes a scalar now. The difference in potential is also a scalar. Potential is a scalar, the difference in potential is also a scalar. You should obtain a scalar. We are using a dot product here. So what is E bar here? It is written as E I cap, right? E is only present, the field is present only along x-axis. So it is of some magnitude in a particular direction I cap. Now, if you use this expression, what does this mean? Delta V equals minus integral. E bar is written as E bar Ex I cap, Ey j cap plus Ez k cap. Generally, if you include three dimensions. And dr bar is dx I cap plus dy j cap plus dz k cap. So if you take the dot product between these two, you get the difference in potential. But this is a little complex integration. So generally we prefer to do it in single dimension independently. So if you write the change in potential, this is of course along x-axis, right? Change in potential you will see as you move in x-axis from one location to another location, how the potential is changing. dV is the change in potential, right, along x-axis. So I am using a small subscript x. Hope you understand. change in potential between two x points. Now we have 2 points x1 and x2. The coordinates are x1 comma 0 and x2 comma 0. This is P and this is Q. Let us find the potential difference between Q and P. We want to calculate PQ minus VP. So how do you do this? Right? So this is the final point, this is the initial point. How do you do this? So this is nothing but our delta Vs minus integral E dot dx. So in one dimension, this is nothing but negative integral of E bar dot dx bar, which is E dot dx, right? The field is along I direction here, so this will be minus integral E dx, right? So let us mark with E naught so that we will have a clear idea. So the magnitude here is E naught. So whenever we substitute, you will have a clear idea. So this is now expressed as E naught I cap, right? E naught is the magnitude. Now this is the function, electric field function, E dot dx. But Ex dot dx, I am taking only the x values. Y and z we are not taking care of now. So what is the field? It is E naught I cap. If you substitute that, the dot product gives you E naught dx. This is the idea. E naught is the magnitude of the field. Now from which location to which location you have to integrate it? Because the final point is Q and initial point is P. V final minus V initial. Now you have to integrate it from initial point, which is P, from x1 to x2. So what do you get? E naught integral dx is x, so it is x2 minus x1, or you can finally get it E naught x1 minus E naught x2, right? So by knowing the field in a particular direction, we can estimate how the potential is changing. From moving from P to Q, we observe a potential difference. Potential can be different as you move along the field, right? And the final potential minus initial potential can be calculated this way. Along a particular direction, if you want to do it in a uniform field, all you need to do is take the component along that direction and perform the integration operation, right? So this is some mathematical analysis. Let us discuss more physical aspect of this relation. So physically, how we understand field and potential? So by definition, we know field is negative gradient of potential. Gradient is nothing but the slope in distance, slope with distance. You know, velocity is a derivative of position, right? We are taking the derivative with respect to time, and again you obtain acceleration by taking differentiation of velocity with respect to time. So though those things are derivatives of time, now here we have something which is getting differentiated with position. See, x, y, z, we have positions. So here we are taking kind of a slope. We are differentiating it, but with respect to positions. If you differentiate the potential function with positions, but you take the negative of it, then you obtain the field components. So particular direction, let us confine to one dimension again, one particular direction. It is simple to understand that way. So let us fix ourselves to x dimension. Now along x axis, the magnitude of field at a particular location, at any particular location along the x axis, anywhere, can be 0.2, 0 or 4, 0 or minus 4, 0, any point on the x axis. You want to calculate the field at that point. That is obtained by the potential information. If you know the potential information, you can do that. What it is actually, it is the magnitude is rate at which potential is falling with distance, right? Falling. See, it is negative of the slope. That means This gives you the idea how potential is increasing, right? For example, if you write dx by dt for velocity, you know how potential is changing with time, right? So this will be positive if it is increasing, if the position is increasing with respect to time, particle is moving ahead and ahead. But if you take the negative of it, that means what kind of idea are you giving? How it is decreasing, right? So it is the negative gradient of potential. That means the rate at which the potential is falling with the distance, not increasing with distance. So if you get dy by dx positive, that means field is directed in negative x direction, right? Right. So dv by dx, let us understand dv by dx. So it is a derivative of potential with respect to x, or change in v by change in x, you can say. This is delta v by delta x. We understand this even better. So if you have a change in x, you move from one point to another point, you will see how the change is happening with potential, and you take negative of that, you get the field. For uniform field, you can write it as minus delta v by delta x, because it is uniform. The changes which happen will be constants. The changes will not change, right? So you can write it as minus delta v by delta x. That means Ex is minus of change in v by change in x position. For uniform field, this is very important. If the field is not uniform, you can directly write it as change. You have to take the differentials. Only for small changes that is true. But for uniform field cases, you can take bigger changes. So now let's go to this example. Here on the x-axis, we know the potential information. Observe carefully that the potential at x equals 1 is 10 volts, at 2 it is 8 volts, 3, 6 volts, and so on. So do you observe any constant change in the potential? Is there any change in the potential with position? As you move ahead on x-axis, 1, 2, 3, increase your position. Now you see that the potential is decreasing, right? What is the change in potential? Let us say we are moving from 1 to 2, right? You move from x equals 1 to x equals 2. What is the change in potential? It is 8 minus 10. Final value minus initial value. By the change in position is 2 minus 1 SI units, meters, it is given in meters, but the negative of this, that is field. This is minus of V final minus V initial by X final minus X initial. Right, 8 minus 10 by 2 minus 1 and negative of it. So what is that? Calculate. So it is minus 2 minus, you get 2 units. The units are Newton meter square. What are the field units? So it is QE, Newton per Coulomb. So this is how you understand the field. The field is the rate at which potential is falling with the distance. Now from this information, 2 Newton per Coulomb, if there is a constant field 2 Newton per Coulomb in I direction, X direction, now what do you understand? From this answer you have to relate it with this or this. Understand the definition. If it is 2 Newton per Coulomb, right, so that means 2 units of electric field strength. in particular direction. Now you should understand, for every 1 unit, potential drops by 2 units, right? The rate at which potential is falling with distance. So if the electric field what you obtain in x direction is positive, that means in that particular direction potential is actually decreasing, right? Potential decreases. So along a field line, if there is a field line, the potential along the field line always decreases. So if it is higher potential and its lower potential, it is even lower, it is even lower, it is even lower. So the potential decreases along the field line. This idea you should have. Potential decreases along field line. So physically, how do you understand the field? Field is if field is in a particular direction, then you should understand that the potential is decreasing along that direction, right? And the rate at which potential is decreasing is nothing but the magnitude of the field, right? So it is decreasing 2 units per 1 unit change. Now the the magnitude of the field itself is 2 units, 2 Newton per coulomb. So if this is slightly different, if I say this is 10, 9, 8, 7, so on, right? In the decreasing order, 10, 9, 8, 7. Now for 1 unit, 1 volt is changing, decreasing. It is decreasing by 1 volt. That means the field strength is 1 Newton per coulomb in x direction. Now quickly you have to do this just by looking at it. If there is a uniform field along x axis and now you have this information, -1, -2, -3, and you observe the potentials are 10, 4, -2, so on, right? Now in which direction is the potential decreasing? In this direction, negative x direction, right? This is positive x, this is negative x. Now in negative x direction, you see that the potential is decreasing, 10 volts, 4 volts, -2 volts. And what is the value? It is decreasing by 6 units, if you can see. For every 1 unit of movement ahead, it is decreasing by 6 units. So the field strength in this direction is 6 Newton per coulomb. In that particular direction, the potential is dropping. So this is the relation between potential and field. It is important. We'll provide a worksheet involving some problems. I hope with some practice you will understand it even better. Let me explain it more clearly. So this is how we visualize the field. So the field is going along x direction, but there is a small change. In one region the field is uniform, suddenly it has become non-uniform, and again it has become uniform, right? In this region, same magnitude, same direction. In this region also it has same magnitude, same direction, but here and here the magnitude is different. Can you tell me where it is stronger? When the field lines are densely packed, the field is stronger. That means here the field is stronger, here it is weaker. First note that. So if you find lines less spaced, more spaced, it is weaker field, but still it is uniform. The field lines are parallel. Here it is non-uniform field. Some changes happen, we don't know why, but the field is now in this region non-uniform. Again it has become uniform, but of a different magnitude. The magnitude here is different. Here it is stronger relatively. When compared to this, it is stronger field. Now we can get a rough estimate by the potential information. Now this is the potential information I have written. At each point on x-axis, the potential is written here. At 1, the potential is 100 volts. At 2, the potential is 80 volts. At 3, the potential is 60 volts. First tell me, are they in decreasing order? Yes. Is the field in same direction? Yes. So this is true. There is nothing wrong in this. In the direction of field, the potential should drop. Potential at each location should drop. It is decreasing. That is fine. And if it is uniform, if the field is uniform, it decreases at a constant rate. And for particular distance, it will fall a certain amount, and that will be constant. See, for each unit, what is the change you see here? The change is decreases by, so here write decreasing information. Here it decreases by 20 volts from 1 to 2. Here also it decreases by 20 volts. And here also it decreases by 20 volts, 60 to 40. So the field is uniform and it is decreasing 20 volts per 1 meter. Right? So that is nothing but the field strength. So in this region, the field strength is E is 20 volt per meter. This is another unit for the electric field. It is same as 20 Newton per coulomb. They are same. Volt per meter or Newton per coulomb. So this is how you get the information of the magnitude. Magnitude is the rate at which it is decreasing with distance. Now observe this, in the non-uniform region, suddenly the field has become non-uniform. That means it will decrease, but it will decrease on a different rate, right? So here if you observe, the change here is 20 volts per meter. Again, it is falling 20 volt per meter. All this, in all of this region, it is constantly decreasing, but suddenly now here it is minus 22 volt per meter, right? Is decreased by 22 volts per meter. We are writing how it decreasing, how it is decreasing. Again, now it has decreased by, I think it is 36 volt per meter. For 1 meter distance, the potential has dropped by 36 volts. It has become into negative values. Somewhere you get the 0 here. See, the potential is becoming 0 here. In this case, the infinity is not our reference. I told you, the infinity case, we take it as a reference in most general cases. But in some cases, the potential can be taken as 0. It is our choice. So here, the potential at this location is 0. So at the infinity, it will not be 0. Right? So if this field goes to infinity, it keeps on decreasing. The field will, the potential will be some negative value at the infinity. Right? So it is keep on decreasing, and then now it has decreased even further. So it is now 40 volt per meter. See, it is increasing. Now once the field has become uniform, observe the changes. Now this is again 40 volt per meter. This is again dropping by 40 volt per meter, and this drops by 40 volt per meter again. For each 1 meter movement, we see a drop of 40 volts. So now it has become constant. The rate at which it is decreasing has become constant. The field has become constant. It is 40 volt per meter. The rate at which it is decreasing. So that is the field strength in this case. See, observe, it is bigger than this. Why? The field is stronger. The lines are closely spaced. And almost the space here and the space here, if you see, this is half of this. That means field has become twice as stronger. It was just 20 Newton per coulomb or 20 volt per meter. It has become double, 40 volt per meter. That means in this region, the voltage, the potential is decreasing rapidly, quickly. For every 1 meter, it is now decreasing by 40 volts. It was decreasing only by 20 volts in this region. This is how you visualize the field and potential relations. This is very important idea. You don't have to solve much complicated problems on this for now. Just try to understand the relation between field and potential. One definition, one simple definition. The field is, the magnitude of the field is nothing but the rate at which the potential is decreasing with position. That's it. So the next topic, equipotential surface. This is related to this relation between field and potential. So equipotential surface is any imaginary surface. We imagine a surface on which the potential is of same value. We have to imagine such a surface that the potential on that surface must be of same value. Everywhere, if it is 10 volts, it should be everywhere 10 volts. So now in our situation, we have been discussing the same thing, x-axis. The field is along x-axis. Now the potential is dropping 10 volts, 8 volts, 6 volts, 4 volts. Now understand, if field is in a particular direction, the potential decreases in that particular direction, right? Along direction of field, potential decreases. This is for sure. This is what we have studied so far. So if field is present in a particular direction, the potential changes and it particularly decreases in that direction. But if the field is not present in any direction, let us say the field is only present along x-axis, so the field is not along y, is not along z, it is only along x-axis, right? So clear this point in your mind. If it is only along x-axis, it is not along y, it is not along z. That means if the field is not along x, that means you should understand the potential will not change along y. If the field is not along z, that means the potential is not changing along z. If the potential is changing, if it is decreasing, then the field component must be present, right? That is how they are related. So if the field is only along x-axis, now tell me, does the field along y vary? This is the question you should ask yourself. Does the potential vary with y? Is it changing with y? No, because there is no component of field along y, it is only present along x. So if you take any point here, the y coordinate can be anything, the potential must be same. That means if you take this point, it should be 10 volts. If you take this point, this should be 10 volts as well. So you get this kind of a line which is equipotential line, right? Do you understand this? So because the field is absent along y-axis, the potential does not change along y-axis. The potential at every y point will be same, right? At a particular x, if you have some value, it will not change with y. Similarly, here you will have 8 volts, 8 volts. Equipotential line, you can say. But what is equipotential surface? Now let us bring it to 3 dimensions, x and y. Now let us discuss about z. It is coming out of the plane. Now is the field present along z axis? No, the field is only present along y axis. That means the potential is only changing along x axis. The field is along x axis, the potential decreases along x axis. The field is absent along z axis as well, just like y. So the potential does not vary with z coordinates also. So that means if you take any point which is outside, but here at the same x value, but z is different, it is coming out. Here the potential will be 10 volts as well. So let us try to draw it in 3D. So I am trying to draw it in 3D. So in z axis, if you take any point, there also the potential should be 10 volts, just coming out, right? Or here in the next step, if you take one point which is outside, if it is 8 volts, at this point also it should be 8 volts, at this point also it should be 8 volts, here also it should be 8 volts. Why? Because along z the potential does not change, only along x it changes. So all these points, as you are seeing, all these vertical planes, 10 volts plane, 8 volts plane, then the 6 volts plane, these are equipotential surfaces. So one such plane is this 10 volts plane. So you will have plane of same potential perpendicular to this uniform field. So the field is along x-axis. You have to take an imaginary surface, a plane, and then that plane will be an equipotential surface here in this case. So for uniform fields, you observe this, because field is only present along particular direction. The other two dimensions will have same potential values. So you will see a 10 volts plane, 8 volts plane, 6 volts plane, and so on. All these planes which are perpendicular to the field direction, or you can say the field cuts the equipotential surface perpendicularly. This is also important. Field cuts, or it pierces, it crosses the equipotential surface exactly perpendicularly. This is also important. If there is an equipotential surface, you should understand that the field is intersecting it perpendicularly, right? If you know the field direction, you should know that the equipotential surface is perpendicular to it. They are the same thing. So this is the information about equipotential surfaces. Let us discuss one case where you have spherical equipotential surface. For a point charge, the field is radially outwards, right? See, it is cutting the sphere perpendicularly everywhere. If you know that the field is cutting it perpendicularly, then that is equipotential. So in the case of point charges, equipotential surfaces are spherical. Imaginary shells, you can imagine imaginary shells around the point charge, and you will see that the field is intersecting it perpendicularly everywhere. At any point on the sphere, this radial vector, it is cutting it perpendicularly. Such a surface is equipotential surface. What does it imply? The equipotential surface, along the equipotential surface, the field is not present. The field is present only in the perpendicular direction. See, it would be a contradiction. If this is an equipotential surface, that means the potential here and here, very close points, two close points if you take on the surface, they are both of same potential, right? So if they are both of same potential, why will the field be present in that particular direction? If the field is present, then the potential should change, right? So in the direction of field, the potential decreases. So in that case, if the field is present in tangential direction also, some component, if the field is present tangentially, it means that the potential is not same. But for equipotentials, potentials have to be same at all points. So that is why the field is completely absent along tangential direction. It is present only along normal direction, right? So that way you can explain the equipotential surface. Along the equipotential surface, there will not be any field component. That is also important. Along equipotential surface, field component is 0. By definition, equipotential means it should be of same potential. So if the points are of same potential, why will the field be present along the surface, right? If field is present, the potential should vary. So it is a contradiction, it cannot be true. So along the equipotential surface, the field component is always 0. You can add always. Right? So this is the information about field and potential difference. All these topics are very important. Try to understand them carefully. Read the textbook if you have. In the next class, we will start with electric flux.